Today we are jumping into a really big topic, calculus. And I know, that word can sound intimidating, but I promise you it's so much more than a math class. It's the language we invented to describe a world that never, ever stops moving. So let's start with the central problem. For most of human history, mathematics was incredible at describing things that were static, things that just sat there. But what about the real world? The world of planets constantly orbiting, economies constantly growing, things constantly in motion. That was a whole different ballgame. You see, for thousands of years, we had tools like geometry for fixed shapes and algebra for fixed relationships. And look, those are perfect if you're building a pyramid, but they're not so helpful if you're trying to chart the path of a comet. We needed a new language, a kind of math designed not for things as they are, but for things as they were constantly becoming. Okay, so here's our game plan. First, we'll talk about this language for motion. Then we're going to meet our two main characters, the derivative and the integral. After that, we'll see how one brilliant unifying theorem brought them together in a shocking twist. And finally, we'll explore how this incredible idea completely remade the world we live in. So let's start with the big picture. How do you even begin to create a language that's built for change itself? Well, it turns out the entire sprawling story of calculus really boils down to just two massive opposing ideas. You've got the derivative, which is a tool for breaking things down, for looking at a single frozen instant. And then you've got the integral, a tool for building things up from an infinite number of tiny pieces. All right, let's meet our first idea, the derivative. This is all about precision, about a tool that lets us zoom in on one single moment in time. The best way to think about this is your car's speedometer. Let's say you drive 120 miles in 2 hours. Your average speed was 60 miles per hour, right? That's simple algebra. But that's not what your speedometer shows. It shows your speed right now, 75, then 50, then maybe 65. That number, that speed in one specific instant, that is pure calculus. That's a derivative. So what the derivative really does is it gives us a way to measure the rate of change in a frozen moment, when basically no time has passed at all. And the way it does this, visually, is by finding the slope, the steepness, of a curve at one single point, which is why it gets that cool nickname, the slope finder. And the way we find that slope, it's just brilliant. First, you start with a simple line that cuts through a curve at two different points. Now, imagine you start sliding those 2 points along the curve, bringing them closer and closer and closer together until they merge into one single point. That line doesn't cut through anymore. Instead, it just barely kisses the curve at that one spot. That new line is called a tangent, and its slope is the derivative. It's the steepness at that one exact instant. Okay, time to meet our second big idea. If the derivative was all about breaking things down to a single point, the integral is all about the opposite, summing things up. So let's go back to the car. If the derivative is the speedometer, the integral answers the flip side question. If your speed was changing constantly during your trip, how far did you actually go in total? You can't just multiply speed by time anymore, right? You have to somehow add up the little bit of distance you covered in every single tiny moment of the journey. That colossal act of summing everything up, that's integration. The integral is basically our engine for accumulation. It works by adding up an infinite number of impossibly small pieces to get a precise final total. Visually, this translates into something really powerful. It allows us to find the exact area under a curve, and that's why we call it the area finder, or even the infinity adder. And the process for doing this is just so clever. You start by just trying to approximate the area under a curve with a few fat rectangles. Obviously, the fit isn't very good, so you try again, this time with a lot more, much thinner rectangles. The approximation gets a lot better, right? Well, the real magic happens when you take this to the absolute limit. You imagine using an infinite number of rectangles, each one infinitely thin. At that point, they perfectly fill the area under the curve, and you get the exact answer. So for a long time, we have these two huge ideas floating around. One finds the slope at a single point, and the other finds the total area over a long interval. They seemed completely unrelated, and then came the climax of our whole story. Just for a little context, people had been working on these ideas for centuries. The ancient Greeks were already approximating areas, which was a kind of proto-integral. And then in the 1600s, mathematicians like Fermat were getting really good at finding tangents, a proto-derivative. But they were always seen as two totally separate, unrelated problems. That is until Isaac Newton and Gottfried Leibniz had a truly mind-blowing realization. And here it is. Here's the big twist. They discovered that these two operations, which seem like total opposites, right? One breaks things down, the other builds them up. They weren't just related. They were perfect inverses of each other. They literally undo one another, just like multiplication and division. This incredible insight is called the Fundamental Theorem of Calculus, and what it says is just profound. It says that to find the total area under a curve, that massive infinite sum we were talking about, you don't actually have to do the summing, because integration is the inverse of differentiation. You just have to find the function whose derivative is your curve and then plug in the start and end points. That's it. It is a miraculous shortcut that transformed calculus from a neat idea into an absolute powerhouse. And this unification didn't just stay in the abstract world of math books. No way. It exploded outwards and completely remade our world by giving us the tools to finally understand and engineer a reality that is always in motion. And the applications are just everywhere. You can see how across physics, engineering, economics, even computer graphics, the core tools of calculus serve as a kind of universal translator, turning real-world problems into equations that we can actually solve. I mean, in physics, Newton used calculus to come up with the laws of motion and gravity. Your velocity is just the derivative of your position. Your acceleration is the derivative of your velocity. And with integrals, engineers can calculate the total force of water pressing against a dam, where the pressure is constantly changing with depth. Over in economics, derivatives give us this crucial idea of marginal cost. What's the exact cost to produce just one more widget? And by finding the point where the derivative of a profit curve is zero, a company can find the precise, exact production level that will give them the most profit possible. And this might surprise you, but it is at the absolute heart of our digital world. You know that stunningly realistic lighting you see in movies and video games? That's calculated using a massive integral called the rendering equation. Cleaning up a noisy audio signal or transmitting data through the air, that relies on something called the Fourier transform, which is all about integrals. So when you step back and look at it all, calculus is so much more than a subject in school. It's the fundamental grammar we use to describe reality itself. It really is the architecture of change, and it allows us not just to see the world, but to predict its behavior and ultimately to build our future. Which really just leaves us with one final thought. We have this one tool to see a single perfect instant, and another tool to see the entire sweep of a journey. The real power comes from seeing both at once. So the question is, what's next? What new discoveries are out there waiting now that we finally have a language to describe both the moment and the journey?